are seeing very important equation today. This is compulsory asked into the 12th board examination. This is very important equation, that is the derivation, and there are problems on this derivation and this formula, and always asked to derive into the examination. This is the integrated rate law equation. Very simple. Now the students which have mathematics, they understood very earlier, but those which student which do not have mathematics subject, but they still if they watch this video and this lecture, then you definitely understand this derivation. Now see, this is the integrated rate law equation for the first order reaction. We already see what is order, what is molecularity, which are the first order reaction. The reactions whose rate depends on only one concentration, that are called as the only one reactant concentration, that are called as the first order reaction. Now consider the first order reaction. A gives products, any products, because we know that in the rate law equation there is no about the products, but we want only the reactants to write the derivation of the rate law. Now the differential rate law, we know that how it is given as, we give that rate is equal to K into concentration of A. As it is the first order reaction, here only A is raised by 1, but 1 is not shown. And we already see that the rate is given as in the language of reactants. As the reactants are consumed, we write the rate that is minus dA divided by dt, because A is the concentration of the reactant. Now this is the square bracket is the concentration as reactant consumed, so the negative sign is given. This is also the rate, this rate. So rate is equal to K into concentration of A. This is from the rate law equation. Now see, in this way the rate is given. Differential rate law you know very well. You understand that the rate of this rate law of this reaction is given as rate is equal to K into concentration of A, as it is the first order reaction. But rate is right in this way in the language of reactant, minus dA by dt. This is already we see saw into the last lecture. Now see here this square bracket, in the square bracket A is the concentration of the reactant at time t. We know that. Now rearrange this equation. Rate is equal to minus dA upon dt. Now suppose the rate is this only, minus dA upon dt is equal to, this is rate, is given as K into concentration of A. Now rearrange this equation. This as concentration of A is here, now it comes to the this left side, concentration of A. Now this is dA divided by concentration of A is equal to, this minus sign goes here to the right side, and K is equal to dt. This dt is here divided, it becomes multiplied to this K. Only we rearrange this equation. Now the A, that is the concentration of A, get divided of dA upon A is equal to, this minus sign goes to the right hand side. So minus this minus sign, minus K into this dt. As it goes to the right hand side, it multiplies the K. Now on integrating this equation, now take the integration of this rearranged equation. Now how it integrated? Now the sign of integration is in this way. This is the sign of the integration. The mathematics subject having student understand very well. Now this is the integration sign, and see here there are limits for the integration. Limits are given. Now when time t is equal to 0, the concentration of A is A0, because at 0 time there is no reaction, and the concentration, this is the initial concentration of the reactant A. Now that is A0. That means up to this initial time when t is equal to 0, reaction does not start. As the reaction starts, the concentration of A becomes concentration of A at time t. After time t, when t is equal to t, that means when reaction start and after time t, the concentration of A becomes At. At the initially, concentration of A is equal to A0, as reaction is not started up to that initial concentration. After time t, the concentration of A is equal to At. Now here A0, concentration of A0 is the initial concentration, and concentration of At is the concentration at time t. Understand that very well. Now these are the limits. So there are the limits for the integration. Now this is the sign of integration. Now we take the integration of this rearranged rate, differential rate. Now I write here d into concentration of A divided by A. Concentration of A here, and again here also take the integration to the right hand side. Now as k is constant and this negative sign is outside of the integration sign. Here also the time at the initial time is 0 and after time t it becomes t time, and integration of dt is here. Now in this sign of integration there is the dt. The limits of time are from 0 to t, and the limits of concentration are from the concentration of A 0 to a concentration of 8. Now this is the limits. Now understand, this is very important. Now see, what is the integration of this dA upon A? Now in mathematics there is the rule. Now that rule is dx upon x integration from the limit, that is the x0, x is equal to 0 and x is equal to x. About that, the integration of such, that is the rule, is ln x, such that from the limit of x is equal to 0 and x is equal to x. Now this is the that is the rule of integration. Dx upon x is equal to integration of dx upon x from the limit x is equal to 0 to x is equal to x, that is ln in bracket x from x0, x is equal to 0 to xx. Similarly here dA upon concentration of dA upon concentration of A, the integration of this quantity is ln concentration of A from the limit A0 to At. In the same way, as this is constant and minus signs are out of the integration sign, so the integration of dt, now there is the another rule of integration of only that is the dx, integration of only dx. What is the integration of only dx? Now see, the integration of dx is equal to only x, and the limit are x0 to x, so 0 to x. Now remember that integration of dx upon x is ln x. Similarly here integration of dA upon A is ln A, but only integration of dx comes x. So here only integration of dt, so it comes t, and from the limit 0 to t. In this way it is written. Now see, this is very important. Now this can be write as, we can write this in this way, ln At minus ln A0. In this way we can write this quantity is written as ln concentration of A at time t minus ln concentration of A at time 0. This is also written as, now see this minus k, I write directly here t, but this is as this comes from t minus 0 in this way, right? As it is ln At minus ln A0, so it can be write as minus k, that is the constant, and t minus 0, but t minus 0 is equal to t, so I directly write here minus kt. Now see, this is very important. Simple steps are there. Integration of dA upon A is equal to ln A from the limit A0 to At. and integration of dt is only t from limit 0 to t. This is the constant outside of that. Now this can be written as at the limit from a0 to at. So it is written as ln at minus ln a0. Similarly, this is written as this minus k is constant, t minus 0. But t minus 0 is t. So that is directly right here minus kt. Understand up to this? Now you know that in the logarithm, now this is ln is the logarithm to the base e. We know that this is logarithm to the base e. So in logarithm, minus of the two logs, that is the division of the logs of the two, that is numbers. Now this can be written as ln at divided by a0. Now this can be written ln at minus ln a0 is written in this way. The subtraction and divisions are written in the language of logarithm in this way. This is logarithm to the base e, at, concentration of at divided by a0, concentration of a at time 0. And similarly here as there is no logarithm sign ln, so it is minus kt is written as it is. Now if we want to this logarithm to the base 10, we want to do the logarithm to the base 10, we know that we have to multiply by which number? 2.303. But this is the first step. Now here we always ask into the examination, into the problems, that is the value of the rate constant k they ask. So how we calculate the value of rate constant k? So take this k to, suppose this k is as it is to this side, and this minus sign comes to here. As the minus sign come here, this becomes log to the base e of a0 upon at. If we do not want to write the minus sign, now this minus sign comes here only k, and this t is here multiplied, it becomes here divided. So the 1 upon t, this becomes 1 upon t. To shift that side, this becomes 1 upon t. This is ln as it is, but there is minus sign. So the one step I delete here. Suppose I give here minus sign, then it as it is ln 80 upon a0. But minus sign get cancelled, so it becomes 1 divided by t ln a0 upon 80. Now this is the equation of the rate constant, but we want to convert the log to the base e into log to the base 10. So only multiply by the number 2.303. So this equation becomes k is equal to 2.303 upon t. Now here log to the base e becomes log to the base 10, and concentration of a0 divided by 80. Now this is the integrated rate law equation. K is equal to 2.303 divided by t log to the base 10 a0 upon 80. a0 upon 80 bandhanakko. Now this I write here again that equation of the integrated rate law. Now see how the equation of that integrated rate law can be written into the different, that is different forms. Now see, k is equal to 2.303 upon t log to the base 10 of concentration of A at initial concentration divided by the concentration at time t. Now this is the integrated rate law equation. This is very important equation. There are always numericals on this formula, and they always give us the initial concentration, the concentration at time t. In the problem, sometimes they may be given the value of time also in minutes, or if we want to calculate time, then this equation becomes t is equal to 2.303 divided by k log to the base 10 of concentration of A0 divided by AT. Now this is the another again form to calculate the time. Now see here, time is given in second, in minute, in hour, or it may be in days, month and years, any. So the what is the unit of this rate constant K? What is the unit of rate constant K? Now see this quantity is only the ratio of concentration. So this quantity do not have any unit, but time have the unit second, minute, that is the hours, days, months and year. So the unit of this K, now T is divided here, so unit of the K, that is the rate constant, are per second, per minute, per hour, per day, or it may be per year or month. In this way, these are the different units of the rate constant K. Because here the unit of time are the second, minute, but here time is divided. These are the inversely proportional. Rate constant and time, we are seeing that these are the inversely proportional quantities. Now see the another form of this rate law. What is the another form of this rate law? See that from the equation, this is the equation which give the another form of this rate law. We know this equation, ln concentration at time t divided by concentration at time 0 is equal to minus kt. This equation we know. Already we see this equation. Now this is converted into the language. How it is converted into the another form? By taking the antilog to both sides. Now take the antilog to both sides of this equation. By taking antilog to both sides. Now the mathematics student know that what is the antilog of this. How we calculate that? If we take the antilog of log, it becomes only 80 divided by A0. You know that. The antilog of the log is only this 80 divided by A0. And there is the rule that is equal to e raised to minus kt. Now this is the logarithm rule. By taking the antilog of this minus kt, it becomes e raised to minus kt. In this way, there is the antilog of this. Now this is another form. If we want to calculate the concentration at time t, this 80, if we, in the that is the problem, if we want to concentration at time t, that is become equal to A0 into e raised to minus kt. Now see this. Suppose this is the first one is the, that is the integrated rate law is the first equation, first form. Now this is the second form of the integrated law. What is that? Concentration of A at time t is equal to concentration of A at initial concentration e raised to minus kt. Now this is the another form. There is again, that is the third form of the integrated rate law. I write here the first form again. The first form of the integrated rate law is equal to K 1 divided by T log to the base 10. Now I erase this and it becomes that is concentration of A0 divided by AT. So concentration of T at time T. Now this is the first, that is form of integrated rate law. Now come to the second form of the integrated rate law. Now see what is the second form. This is the second form of integrated rate law and it is equal to AT concentration of A at time T is equal to A0 into e raised to minus k. Now suppose into the another language, suppose small a is the initial concentration. Now I write here A0 is equal to A moles per dm cube. Now this is the initial concentration, A moles per dm cube. And after time t, the concentration, now this is the at time t is equal to 0. Now after time t, suppose x moles of A are used up or consumed. Then how many moles of A are there into the reaction mixture? Now that is the concentration of A remains, that is the AT, that remains. Suppose X moles of A are consumed. X moles of A are consumed.
माझ्यावरचं डाटा संपलेला आहे असं मेसेज आला होता, तर हे चालू आहे, मग चालू देऊ का?
Now see here, AT is equal to, now what the AT remains after time t? A minus X moles only are remains. So A minus X moles decimeter cube at time t is the concentration which is remaining. चार्जिंग संपलं होतं का?
त्याच्यात असं म्हटलं होतं 90% तुमचा डेटा वापरला गेला, एअरटेल थँक्स ॲपवर तुम्ही हे करावं असं तसं म्हटलं.
येथे काहीच करू नको,
काहीच नाही चालू.
Now what is the near rate law? Now the third form of the rate law is given from this. K is equal to 1 divided by T log to the base 10 of A concentration. A moles are there, so A divided by A minus X. Now this is the third form, and this third form is also there are the problems on this third form of the integrated rate law. Now see, these are the three different forms of the integrated rate law of the first order reaction. Very important forms. All these are three. Then we have to see here about the that is half-life period of the first order reaction. How the half-life period of first order reactions are calculated. Now see how it is calculated. Half-life period, we have seen the half-life period of the first order reaction, how it is calculated, and which is the formula for the half-life period. I write here half-life of the first order reaction. This is also very important. Half-life period of first order reaction. Now this half-life period of first order reaction is given by the sign T half. Now this is denoted by T half. It is represented by T half, and how it is calculated. Now take the integrated law of first order reaction. We know that K is equal to 2.303 divided by T log to the base 10 of concentration, initial concentration divided by concentration at time t of A. Now this is our integrated rate law. Now after the half times, when the concentration falls half, of initial concentration falls half. Now what is the value of AT after the time t? T half. Now substitute here. T is equal to T half, and the initial concentration A0 becomes A0 divided by 2, because the concentration of A becomes half, falls half, or consumed half. So it becomes the concentration after half time becomes T0 divided by 2. And substitute this value in this equation X. Then what is the rate law for the that is first order reaction? That is the half-life period we can calculate. K is equal to 2.303 divided by T half log to the base 10. Now here is the A0 is here, and divided by this 80, sorry, this time after half time this becomes AT becomes A0 divided by 2. So substitute this value of AT in this equation. Here it is A0 divided by 2. Now this A0 get cancelled, and this 2 goes to here. and the equation becomes k is equal to 2.3 not 3 t half log of 2 here. Now this is the log of 2 is 0. That is the 3010. Then this equation becomes k is equal to 2.3 not 3 upon t half into 0.3010. Now this is the log of the 2, and after multiplication of this it becomes k is equal to 0.693 divided by t half. If you multiply this 2.303 and 0.3010, then the value is 0.693 divided by t half. Now this is the equation to calculate the rate constant if we know the half-life period. But if we do not know the half-life period and it have to calculate it by the equation 0.693 divided by k. Here if we know the value of rate constant, we can easily calculate the half-life period of that reaction by this formula. Now this is also very important formula to calculate the half-life period of the first order reaction. This is also very important, and there are some graphical representation for this first order reaction. If we take the equation that is half-life period, then the first order reaction is independent. Now see here, there is no concentration term in this equation of the half-life period. That means what? The value of half-life period is independent on the initial concentration. Now graphically we can also prove this equation in this way. Now you understand that this is very simple, and if we put the value of time at t half and the value of that is the concentration remaining at time t, that becomes half, consume half, so A0 divided by 2, and if we put these two values in this x equation, then our equation becomes k is equal to 0.693 divided by t half, and if we have to calculate the half-life period. Now this is the formula. Now come to the graphical representation of this half-life period of the first order reaction. How the graphical representation? If we draw the graph, or if we plot the graph of initial concentration versus time, then the graph is in this way. Concentration versus time, the graph is in this way. So this is here, suppose there is the concentration of A and here is time, then the graph is in this way. What this means? This means that that is the half-life period of the first order reaction is independent of the initial concentration of the reactant. This is shown by this graph. The initial concentration, there is no dependence of the concentration, because in the formula of the half-life period there is no concentration term, so there are only the half-life period, rate constant, and this, and from this graph it is also that is proved. Now the graphical representation of first order reaction is there. This is the graphical representation of half-life period of the first order reaction, and if we want only the graphical representation of first order reaction, graphical representation of first order reaction. If we plot the graph of for this equation, rate, now the reaction is A gives product, so the rate is equal to minus D into concentration of A divided by dt, and it is equal to, that is the K into that is K into dt. Sorry, concentration of dA upon A is equal to minus K into concentration of A. Now On rearranging this equation, it becomes minus d into concentration of A divided by A, that is equal to K into dt. Now on rearranging this equation becomes K into dt. Now from this we can calculate the that is the graphical representation we can give. Now see, suppose this here is addition of C. Now this equation is the straight line equation. Y is equal to mx plus C. The straight line equation is equal to y is equal to mx plus C. This is the equation of straight line. And if we match this equation or compare this equation, this is the y quantity, K is equal to m. Now this is dt and this is intercept. Here is the intercept 0. This graph of this equation must be straight line and passing through the origin. So the graph of this equation is given in this way. That is, if we plot the graph of rate versus concentration, initial concentration versus rate. Here suppose concentration and here is the rate of the reaction. Then the graph is a straight line passing through the origin. This proves that this is the straight line equation, minus dA upon A is equal to K into dt. And again there is the some graphical representation by rearranging this equation. How it is that if we plot the graph of log of A0 upon AT versus time, it is also straight line, but there is the intercept for that. And if we plot the graph of A0 upon AT versus that is the rate constant, then it is also the straight line graph. In this now this is the that is the second form. Now graphical representation of first order reaction. First form we see that that is if we plot the graph of rate versus that is the concentration, and it is the straight line graph passing through the origin. Now this is our integrated rate law of first order reaction. From that we can give the another graphical representation, second graphical representation of the first order reaction. Now K is equal to 2.303 divided by T log to the base 10 of A0 upon AT. Now this is the integrated rate law. By rearranging this equation, how it becomes? Now this K, now here is the T which is divided of 2.303. Now it goes to here left hand side, it becomes multiplied. So KT and this 2.303 becomes divided. So K into T divided by 2.303 is equal to here remaining this quantity, but this quantity can be written as log to the base 10 of A0 minus log to the base 10 of AT, because this is the division and there is the that is subtraction. We can convert the log into in this way. Now KT divided by 2.303 is equal to log of A0 minus log of AT. Now take this quantity, that is a log of AT, to the left hand side. What that becomes? Log of AT is equal to, now this negative sign of this AT goes to here, minus K into T upon 2.303. Suppose this log to the base 10 of AT remains at this side, this negative sign of this goes to this side, and it is becomes minus K into T upon 2.303. Now this log of A0 which becomes, that is the negative, but the negative sign comes here, so this become log of A0. Now if we compare this equation with the straight line equation, y is equal to mx plus c. Now here this is the quantity y and it is slope is minus K upon 2.303. This is the slope and this is the intercept. Now x corresponds to T and m corresponds to minus K upon 2.303. This is on the y axis, this is on the x axis, and this is the intercept. Now see, how is the graph is there? If we plot the graph of this quantity log of a0 upon 80 versus time, then the log is a straight line, but as there is intercept, so this is not passing through that origin. Now this is also proved by this second graphical representation, the first order reaction. Now again there is the graphical representation remaining. Now see the third graphical representation of this first order reaction. Now we very well know the integrated rate log K is equal to 2.303 upon T log to the base 10 A0 upon 80. Now if we rearrange this equation in this way, now this log to the base 10 of A0 upon 80 is remains at to this side. This T get multiplied to this K and this get divided 2.303. And here plus 0 suppose, that is the intercept C is equal to 0. As the intercept is 0, definitely the graph is passing through the origin, and this matches with the straight line equation y is equal to mx plus c. Now y correspond to this, slope correspond to this k upon 2.303, x correspond to t, and here intercept is 0. So if we plot the graph of this concentration of a0 upon a2 versus concentration, then the graph passing through the origin and which is the straight line. Now this also prove the that is the graphical representation of first order reaction. Now there are the three graphical representation of the first order reaction and one graphical representation for the half-life period. Now this is very important, always asked into the board examination. So see this video very thoroughly and study this video thoroughly and watch and study very concentration with the concentration, because there are the question on this topic, that is the derivation of the first order reaction integrated rate law, then the graphical representation, derivation of the half-life period of the first law. All these are always asked into the examination. So watch, like, share also, and that is subscribe this, all the students subscribe this video.